Hello, welcome to everyone to my YouTube channel TE Academy. Today we are going to discuss about the AC and DC characteristics of op amp, which is also known as operational amplifier. First of all, we should know what are the AC characteristics of the operational amplifier. Many things like frequency response, slew rate, CMRR, PSSR, these are the ratios which can be concluded into the AC characteristics. Now, after this, we have to know what is the frequency response, how it is becoming characteristics of the operational amplifier, what is slew rate, what is CMRR, and what is PSRR. So we will learn it now. The first thing which is it's like frequency response. The frequency response of an operational amplifier is just like the approximate open loop gain versus the frequency, as it we provide it in the graph C. So this is gain in dB. It's a frequency going on. We can write it as frequency in hertz, and you can feel a sudden drop here, F1, and then again a drop. Here it's F2, F3, and F4. Okay, here it is 20 dB, minus 20 dB per decade, minus 40 dB per decade, and here minus 60 dB per decade. As the frequency response of an op amp in a graphical representation, here as shown it as the provided for input signal at a different frequencies. Now we will get to the second point, which is slew rate. You people will be wondering what is a slew rate. Let me define it for you. A slew rate, maximum rate of change of voltage with time. So slew rate is nothing but a maximum rate of change of voltage with time. It is expressed as voltage per microsecond. Now the third one, as I have said you, CMRR. What is the full form of CMRR? So let me explain you what is the full form of CMRR. CMRR is nothing but common mode rejection ratio. So you people will be wondering about what is a common mode rejection ratio. Okay, so it is defined as a ratio of differential mode gain to the common mode gain, that is CMRR equals to A differential mode by A common mode. So as we have seen, what is CMRR? Common mode rejection ratio, the ratio of differential mode gain to the common mode gain, represented mathematically as ADM, where DM is a differential mode, by ACM, where is gain of common mode. Now the fourth one, it's like PSRR. So you people would be wondering what is the full form of PSRR now. So I would clear it off as power supply rejection ratio. Power supply rejection ratio. Now you people will be wondering what is power supply rejection ratio? It's nothing but a change in input, like a change in input offset voltage Vi now input of op amp due to change in supply voltage. It's like mathematically how we can write it as SRR equals to Vi now by del V. As it has been written or defined by me, it's like PSRR equals to power supply rejection ratio, which can be stated as change in input offset voltage Vi input of op amp due to the change in supply voltage. Mathematically, which is as SRR supply rejection ratio equals to change in V input by change in V. Now we will go through the DC characteristics as we have been completed through AC characteristics of it. Now, DC characteristics. Characteristics. The DC characteristics of operational amplifier. So as we were having a number of like four different characteristics in the AC. Now how many characteristics would be there into the DC? Like it's nothing but input bias current, input offset voltage, input offset current, and thermal drift. So these things we will be going to learn about them now. So first thing what I have said you, it's like input bias current. Okay, input bias current. Now you people will be wondering how to define it. So input bias current is nothing but the current that conducts the current that conducts through the input terminals terminals of the op amp so as to bias the input transistors, where it is given as IB equals to IB minus plus IB plus by 2. Input bias current. The current that conducts through the input terminals of an op amp so as to bias the input transistor, which is given as mathematically IB equals to IB minus plus IB plus by 2. Now the second one was like input offset voltage. Input offset voltage. So input offset voltage is nothing but, I will say it as the, suppose for example there are two transistors that form a differential amplifier in the input circuit of an op amp may not be identical, and hence the difference in their bias currents. So if the currents corresponding to the inverting and non-inverting terminal are IB minus and IB plus respectively, then the difference IB plus and minus IB minus is called input offset current. So as here, it's a inverting and non-inverting input currents, whereas the differences between IB plus and IB minus equals to input offset current, where IB plus is nothing but the inverting terminal and non-inverting terminal respectively, which is IB minus. Third one is that output offset voltage. Output offset voltage. Output offset voltage. Output offset voltage is the output voltage produced due to the input bias current or the input offset voltage. It is the output voltage obtained when both the input terminals of an op amp are grounded, like V output equals to 1 plus RF by R1 VIOS plus RF and IB. VIOS is nothing but input offset voltage. This is input offset voltage, and IB here is input bias current. Now we can write it VOT equals to 1 plus RF by R1 VIOS plus RF IOS, where IOS is input offset current. IOS equals to input offset current. The last but not the least, or we should say the DC characteristics of a op amp is the thermal drift. Thermal drift. Thermal drift is nothing but the change in the bias current. The change in the bias current. Offset current and offset voltage with temperature. Temperature. So what is thermal drift? It's like the change in the bias current, offset current and offset voltage with temperature is known as thermal drift. So for reference, you people, here I ended with the DC and AC characteristics of ideal op amp. Here you people can have a screenshot of this for further making out your notes. So I wait for 2 seconds for you people to have a screenshot. Now the DC characteristics. Thank you and have a nice day.